Today, we're going to talk about how to do kinematics in 2 dimensions. So the initial problem is a ball rolls off a cliff, and the cliff is 1.3 meters tall, and the ball lands 1.5 meters away from the edge of the cliff. So the first thing we need to figure out is how fast was the ball moving when it left the cliff. So set up our XY table with our variables. In the X column, we only need dVt because it's constant velocity. In the Y column, we need V0, VA, dt, because it's all the variables. There will be acceleration in the Y column. We know that since he's leaving perfectly horizontally, vertically he's going to have no up or down velocity, so he's going to have a V0 of 0. We know his acceleration is going to be -10, like all free-falling objects. We know his displacement is -1.3 meters, because that's how far he falls. We know horizontally he has a displacement of 1.5 meters, because that's how far the ball travels horizontally. So the first thing we need to do is solve for our time. We can use our simplified don't need V equation, which is d equals -5t squared, or in other words, -1.3 equals -5 times t squared. So divide both sides by -5. Okay, so that -5 cancels out. So 1.3 divided by 5 is 0.26 equals t squared. And then we're going to square root both of those sides and get that t equals 0.5099. So now we can put that t right here, 0.5099, and we can solve for v. Now in this case, we're just going to use the v equals d over t equation, or in other words, v equals 1.5 divided by 0.5099. So 1.5 divided by that number, and we get that v equals 2.9417. All the 5 digits just for fun. Now, the twist to the problem is after we've done all that, we're going to bring in a, let's say, 40 centimeters or 0.4 meters tall pipe, and we want to place that at a certain distance so that the ball will land at the top of the pipe instead of on the ground. So we have to make a new XY table where dVt, V0, VA, dt. And the struggle people have is understanding which variables are still the same and which are different. So we no longer will travel as far to the left, so we're going to have a different x displacement. We're no longer going to travel the same amount of time, but we will still have the same velocity of 2.9417. Okay? Our V0 is still going to be 0 in the vertical direction. Our A is still going to be -10. Our Y displacement is now going to be 0.9. We get that from doing 1.3 or it should be -0.9, sorry. We get that from doing -1.3 plus 0.4, because we're going down 1.3, but we're not going all the way down to the ground. We're coming back up 0.4. So our displacement is 0.9 negative. So same thing, we're going to solve for t first. So d equals -5t squared. So our d is -0.9 equals -5 times t squared. So divide both sides by -5 again. So we get -0.9 divided by -5, 0.18 equals t squared. Square root both sides of the equation, and we get that t equals 0.42426. Now we can take that number and plug it in here, 0.42426, and we can use the TV equals D equation, and so we get that number times our old velocity times, let's see, 0.42426 times 2.9417, 2.9417, and we get that our displacement is now going to be 1.248. So instead of going over 1.5 meters, we're going over only 1.248 meters. And that is how we solve and do the lab next time. This has been an example of two-dimensional kinematics. Hopefully that makes sense. Thank you.